Mauro Paternostro. He's joining us from Palermo University and Queen's University of Belfast, and he's a leading figure in quantum information, quantum thermodynamics, and optomechanics. And our next speaker, who's going to follow him, is going to be Professor Luis Sanchez Soto. He's a distinguished quantum theorist from Universitat Complutense de Madrid and the Max Planck Institute, and he has advanced the foundations of quantum optics and information. His work bridges fundamental theory with cutting-edge applications. So now it's my pleasure to introduce Professor Mauro Paternostro.
Hello, everyone. Hi, can you hear me all right? Yeah. So I typically shout. Is that all right? Okay. So thank you so much for the kind introduction, and thank you for sparing the time to be here and listening to my talk. And I'm grateful to Osgur and Koch University for the kind invitation. So yeah, I'm Mauro from say a classical superposition of two islands, Northern Ireland and Sicily in Italy. And my task is that of talking of or introducing in a way quantum computing and simulation. So when I received those girls' invitation to come here and talk about at this summit, I told it to my wife. She's a very pragmatic woman, and she asked, "Are you qualified? Yeah, are you really qualified?" So I started thinking, "Am I qualified?" and I started looking at, say, at whether or not I am. And so probably the answer comes from this girl, right? So this is Sarah. She was 9 at the time of this photo. She's my daughter. And I know what you're thinking. You look at her, you look at me, and you wonder, how is it possible, right? Yeah, my wife is a beautiful lady. That's the reason. Yeah. So at that time, she was tasked with a homework at school, and she wrote something along these lines. So my dad works on things that nobody can see, writes weird stuff, and swears a lot, often to his computer, which is right. And then she keeps going on saying it keeps getting worse. And it was much more fun the first time I met him. This explains why, at some point, we received a very worried phone call from a teacher asking, "Is it everything all right at home, really?" So basically, I'm doing weird stuff on a computer, swearing a lot on it because it doesn't work the way I want. But when I don't swear at my computer, we work in a number of topics. In Palermo is a large theory group working in a range of fields that have a very strong overlap with the interests of the quantum group here in Koch. So we work on the foundations of quantum theory, on quantum information theory, on quantum machine learning, which is a topic I will cover briefly in this overview talk. And then there are overlaps with metrology, strong overlaps with thermodynamics, which is a specialty of Osgur's group here. And then more cavity QED, waveguide QED related fields. And my own personal interest overlap with these five fields. So roughly speaking, I should have enough to explain a bit of what quantum computation is. And I will start with this gentleman. So you know who he is? Pablo Picasso, the painter, right? The artist. So great artist, yes, great artist, but not really someone versed into computing and physics, because some point he claimed that computers are useless. They only give answers, right? So, and that definitely don't like as a statement. And there are evidences that show that Picasso was wrong in that. And of course, I mean, what do you expect from someone that portrayed his own lover like that, right? So, and he liked her, right? Guess what he would have done if he didn't? So let's see why Picasso was wrong when referring to computers. And we start with this man, Alan Turing. Alan Turing was a computer scientist, a British computer scientist is the main responsible for the breaking of the Enigma machine, no? The cryptographic device that the Germans, the Nazis, were using during the Second World War. And a leading, say, personality in computer science, and someone that has really laid the foundations of what today we call quantum computer science and quantum information processing. So at some point, he claimed that I propose to consider the following question: is it possible for a computer to think? Which, as a question, is already a very remarkable one that points towards the fact that the view by Picasso was probably too narrow to be serious, to be true. Then at some point, this man comes in, Feynman, that in a very well-known talk in 1959, that was then put on paper later on in 1981, claimed that nature is not classical. And then, damn it, and you can hear him saying that you'd better build, or you better make it quantum mechanical, which hints at the possibility of leveraging quantum mechanics to give a description of nature that goes beyond what you would do with classical computing devices. And then the third personality in this, panorama of why, or argument of why Picasso was wrong, there is David Deutsch. He's a physicist, a computer scientist working in Oxford. In 1985, so he very aptly commented, saying that computing machines making use of the laws of quantum theory are in principle buildable, realistic. Okay, so this opens really a number of questions from the interplay between AI, right? So we are abusing the terminology these days, and computation, all the way to the interplay between quantum mechanics and computation. So Picasso was wrong, in my opinion. Qubits 0, geeks 1, so we are on the lead at this stage. Okay, 1985 and the 80s in general are a great time for people working in the area we are working in, because that's when people realized that quantum mechanics and information theory, two at that time seemingly disconnected fields, can conjure together to build what is now known as quantum information science. And that started somehow the second quantum revolution that Professor Loix referred to no later than a few minutes ago in his press interview. So in this revolution, the interplay between quantum and computing science and computer science seems to be the crucial point. Okay, but what for? Okay, so why should we be concerned with such an interplay? Which sort of opportunities are open in that, say, gray area, gray zone between these two fields? And the first motivation, so I will present a couple. The first motivation is the so-called big data challenge. Now we live in an era where data is produced at an humongous rate. No? Every day, so we process or store something like 100 exabytes of data. That's probably more than what has been produced by mankind up until now. Okay, and this rate is growing by roughly 20% by the year. So we are, I mean, as an example, pre-Trump, the NASA Center for Climate Simulation stored 10 to the 22 bytes of climate observation simulation on superconducting clusters. This is a huge amount of data and information. And having all this information will be pointless unless we develop new ways to analyze, mine, interpret this data in an efficient way. The second motivation stems from size, okay, small size challenge, and was somehow introduced and pointed towards by this gentleman, Gordon Moore. Gordon Moore was an engineer in mid-60s, came up with the so-called Moore law, right? So stating that every 18 months, basically, the size of the elementary constituents of a computing processor shrinks by a factor of 2. Okay, so going on like that, you can think of computer architecture where the elementary constituents become very, very small and you can pack more of them in a single unit. And you can make them, so if Moore law goes on as expected, and we are already seeing some deviations, so there's probably going to be an adjustment to the trend that this diagram shows. We will go down to size and scales that are roughly comparable to those of small molecules or atomic systems. And this is the scale where quantum mechanics comes in. Yeah? So we better make a description of quantum computational processes that is inherently ab initio quantum mechanical, because that's the way we are going to. No, that's where we are going to, and this enables the exploitation of that phenomenon that Professor Loix explained very well in his presentation, in his talk, the superposition principle. So, given that already the difficult part was done by Professor Loix, I will just fly through it. We can exploit the possibility, genuinely quantum mechanical one, creating quantum systems, preparing quantum systems in physical configurations that have absolutely no classical counterpart, where the physical degrees of freedom of my system coexist in distinguishable, say, configuration, right? In a superposition, a quantum superposition state, I can prepare an atom like this one. This is a cartoon, is a stupid example. An atom that is in a red configuration and in a blue one, and these two evidently distinguishable states can coexist simultaneously. This possibility has been certified in a number of experiments, probably hundreds of experiments in the lab. And that's what we exploit when we make use of the quantum parallelism that Professor Loix mentioned. No? So if I make use of a classical computational device and I want to calculate 7 plus 15, then what I do is that I encode this information in a physical configuration of my computing device. I let it process, I get the outcome, and the outcome is hopefully the right one, encoded again in a physical configuration of my processors. And if I have many inputs, then what I have to do is to sequentially prepare such input states in distinguishable physical configurations of my computing device, let it process one by one, and reading out one by one. But if I have a quantum computing device, like the one that we would like to build and that people are working upon, then what I can do is to prepare a physical configuration of my computer that simultaneously encodes all these inputs. So they are all there at the same time. They get all processed at the same time, and they give me a superposition of outcomes that then would have to be read out as Professor Loix mentioned. So this is much more than promising, because if I scale up from two configurations to tens or hundreds of physical configurations of, if my computational register grows up to the order of something like 30 elementary constituents, then already I have the computational power comparable with that of a tier 1 supercomputer. And if I go up all the way to 300 of these constituents, then I will have the possibility to encode more data than atoms in the entire universe. So we have a lot of room to play with. The problem is to manage these numbers in a realistic, in a controllable experiment. So great superposition principle is indeed the key. Can we scale it up the way we explain? Can I build up, massive macroscopic quantum mechanical states that are akin to the paradox that Erwin Schrödinger, so the smiling gentleman in the picture, one of the fathers of quantum mechanics, and a pioneer in the vision that we are now trying to realize. So back in the 30s, he postulated the possibility of building quantum mechanical superposition of macroscopic objects, as macroscopic as a cat. And now as an aside, right? So one of my heroes is this man, John Bell. Is not the one of the telephone, nothing to do with that. Quantum mechanical physicist, quantum mechanics. The guy was from Northern Ireland, a few hundred miles from the university where I was working at until a couple of years ago. And Bell was a vegetarian and an animalist, so he was a pet-friendly person. And so he didn't like the version of the cat paradox that Schrödinger came up with, where the cat either lives or dies. He didn't like that. So in his version of the cat paradox, the cat is either fat or thin, yeah, at the same time. And I'm also a vegetarian, so I stick to that version rather than the Schrödinger one. We should stick to that and feed our cats. So please feed your cats. Okay. So can we scale up to that? And this is very timely. So timely that this year, Professor Lloyd mentioned it, the Nobel Prize for Physics was awarded to these three people, John Clark, Michel Devoret, John Martinis. And the motivation for the Nobel Prize is a piece of art, I think, in that case. So for the discovery of macroscopic quantum mechanical tunneling and energy quantization, so macroscopic quantum effects in electric circuits, that's beautiful. It's exactly what we need. Quantum effects, genuine quantum effects, on objects that are as large as an electric circuit, right? Stuff John Clark says you can put your grubby finger on, right? So stuff that you can see and touch. Right, so as macroscopic as that, maybe not as macroscopic as my cat, I have a rather fat cat at home, but big enough to be considered macroscopic. Potential advantages of these. So you build up a quantum program on a large enough register, like the mess that you see there, that puts together elementary information carriers and processes them according to a quantum program, which is a classically controlled execution of a sequence of quantum operations. And a quantum circuit in its entirety is an ordered sequence of such gates, exactly those that in information technology you use to build, in electrical engineering you'll use to build up your electronic devices. So those building blocks of these complex architectures are the quantum mechanical counterpart of the classical gates that we use in information technology. Why dealing with that? So why bothering with the complexity of building up such macro scale size systems for computational purposes? When you deal with computational processes in a quantum mechanical way, less resources might be needed to process information. So you might get an advantage, a speed up in terms of the time for computation, that quantum parallelism that we explored, or the number of gates that you need in order to process the information itself. And all of a sudden, some computationally difficult problems really in complexity theory become, for classical computation, become much easier quantum mechanically. And we do have instances. Factoring is one of them. And this is crucial for your security. So the security of your PIN codes, your passport, your passwords, your encrypted messages sent on WhatsApp, end-to-end cryptography, your bank account, all rely on the difficulty of factoring large numbers. RSA, which is the most popular and secure cryptographic system that is exploited so far, is based on factoring, which is hard, but that becomes much easier to break the moment Shor's algorithm that was perfectly introduced by Professor Lloyd comes in. While classically you need an exponential time to break, so to factor a number, so the larger the number that you want to factor, the more time, the longer you will need in order to factor it. How longer? Exponentially longer. So an exponential function is a function that grows incredibly fast. Yeah. Quantum mechanically, that growth is still there, but is only polynomial. So we gain a lot. It's a lot slower. Okay, so much less complex to factor than in classical scenario. And the second instance, again, I'm presenting them as from an historical viewpoint. These are probably the first two instances of algorithms that show a clear advantage with respect to classical counterparts. Is the search algorithm by Grover, right? So think of looking. No one uses phone books anymore, right? So, but go back to the phone book, right? So when you add to the youngsters in the room don't know what I'm talking about, yeah. But you had to look for the number of the person you were interested in, and you didn't know in which way it was. So what you did was opening it in the middle and checking. So is the name on the left-hand part of the phone book or on the right one? And you decided, okay, so and then again, and again, and again, dichotomically, right? That's a lot of steps. In fact, it grows like n. Yeah, so no, you need n steps to find the solution. Quantumly, you gain a square root of it again. So it doesn't look like a big advantage. It is. Yeah. These are only two examples of something that has grown to a number of opportunities, go very much beyond basic science and geek-related issues or controversies between cubists and computer science, quantum computer scientists. The possibility of exploiting quantum algorithms for computation has repercussions at the level of national and economic security. So quantum computers, as I said, could break currently used encryption systems, and they have repercussions at the level of both basic and applied science. So fields like quantum chemistry, material designs, pharmacy, or pharmaceutical applications, protein folding are all domains that make use of quantum mechanics and that can benefit from a quantum mechanical approach in the sense of the availability of quantum computational devices able to speed up the process, for instance, of processing data, processing information, for finding the ground state of a molecule, designing new drugs, or understanding, simulating the properties of materials that we cannot engineer as yet in the lab. Broad non-computing impacts in sensing and detection. I think Luis will cover sensing and metrology in his talk, so I leave the task of addressing these beautiful problems to much better hands than mine. So perspective. Should we have a quantum sort of high performance computing devices able to process information and simulate complex dynamics, then we will have a new way of addressing ICT, information and communication technology, to manage energy, to analyze the mass of data that we get from climate observation, to improve security, and also, and I'm sad to say so, but given the international conjuncture, well, it's very apt, we will have military repercussions, certainly. Okay, so these addresses all domains, all areas of our activities or our daily activity. So future computing technologies will open new avenues for computation, for data analytics, for machine learning, opening genuinely new field for a number of basic science topics that are taught at universities, including Koch, and that will build new professional figure. So new technologies will be required for practical quantum computer. New materials will be needed. New fabrication capabilities. The manipulation of the elementary constituents of a quantum computer will need to be improved. We will need to make it fault tolerant. We will need to develop quantum software. We will need to develop large-scale cryogenic capabilities to have available better materials, quantum control that go beyond classical control capabilities, and integrate all that into single manageable devices. For that, multiple disciplines will be necessary, will be needed, from computer science to applied mathematics to information science, physics, of course, but also material science will be heavily involved. And in the end, we will need to develop a figure, no, a new, let's say, profile, which is that of a quantum engineer. Many universities are developing now curricula explicitly dedicated to quantum engineering. The platforms that are currently used for quantum computing are various and numerous, from trapped ions to MV centers to superconducting devices, dots, so semiconductors, and linear optics. And superconducting devices, again, leverage and hinges on the Nobel Prize for Physics of this year, because these three gentlemen have laid the foundation for the first demonstration of the exploitability of superconducting systems for quantum information processing. John Martinez was the first author of a seminal paper demonstrating a special feature, a special type of information processing device called the phase qubit, that has now been developed all the way to what is called the transmon qubit, which is the elementary building block of commercially available architectures for quantum computation. Looking ahead, very much likely a genuinely and uniquely quantum architecture will not be what we are going to exploit. It will be some sort of hybrid architecture that puts together a quantum control unit controlled and interfaced to a conventional CPU architecture that makes use of the best features we have of high performance computing. So you are taking the best of two worlds, the quantum and the classical one, to develop an hybrid version of a computational device. So the 80s established the birth of QIS, of quantum information science. Where are we now? We are in the so-called NISQ era, the noise intermediate scale quantum era. So where we start somehow making compromises on the quality of our devices, still achieving advantages with respect to classical information processing. So in the NISQ area that we are living at, we are implementing the first sort of quantum simulation. Okay, so devices that are able to use quantum processing units to measure and process faster than any simulator based on a high performance computing device. We are making use of machine learning to run quantum neural network capable of learning patterns better than classical counterparts, and we are performing optimization tasks, again based on quantum algorithm. And this topic of quantum machine learning is really, really tantalizing, because people are exploiting really the interplay between what we know of machine learning classically and what we would like to do quantum mechanically. So in this gray area where you make use of well-established machine learning tools to run quantum problems, we are taking a lot of, let's say, fruits that are not necessarily simple to address, and that will be, apologies, this slide was not supposed to be there, and that we are opening up new perspective. There are challenges at the hardware level. Say, photonic architecture are not currently in the NISQ, a NISQ fit. Quantum annealers are capable of simulating large-scale problems, but are limited in the programmability and in coherence time. Electron spins, quantum dots, semiconductor-based technologies are still at an early stage, so we need to demonstrate scalability. And as for topological quantum computation, which is a very, very, very difficult to explain topic, well, we still have only one kind of qubit that has been demonstrated in a controversial matter. So if you build some sort of diagram putting together product maturity towards, say, progress or foreseeable progress, well, there is a number of efforts performed very remarkably by a number of companies that cover basically this entire diagram. Okay, different companies are exploiting different sides of quantum processing capabilities, evolving at a very fast pace. So the Google Sycamore processors, which was one of the first demonstrated once, so acting genuinely quantumly, and Google claimed providing a gap, a witnessable gap, with classical computational capabilities is now no longer state of the art, and that's interesting. So there have been developments, and there is there is a great interest in going towards fault tolerance, which means the embedding of fault resilient techniques in the computational capabilities of your device. Sorry for that. So in this context, what is interesting is looking at the IBM roadmap towards a quantum computer. So this is basically the grand plan that IBM has to build up sizable, nearly macroscopic scale, sized quantum computing devices. Up to 2025, the roadmap has been followed very closely, and now what they are looking at is to 2030s to implement logical qubits, logical information carrier that are genuinely fault tolerant in the device. There are a number of initiatives led by governments. So a number of countries have put quite a sizable amount of money in the development of an ecosystem for quantum computation, including my country, including Italy, which reacted very, very late, but it's catching up. And in this context, I think these sort of initiatives in a country like Turkey are indeed relevant to put countries in the picture of this global scale effort towards the building up of quantum computational capabilities. At the European level, Euro HPC is verging towards quantum computational capabilities. So this is a Europe scale network for the development of high performance computing capabilities with quantum computational ambitions. And this gives the measure of how interesting this is and how much effort is being put in a market that has huge potential for growth. So this is a slide taken from the McKinsey report in 2023 on the quantum technology market, predicting something like $100 billion of US dollars for potential of quantum technology market in 2040. Likely these numbers have to be rescaled now given the difficult conjuncture that we are living at, but gives you the measure of how big this market is going to be in a very, very close future, and how strong is the need to develop a skilled workforce for tackling the challenges that quantum computation is putting to us. Okay, with that, I thank you for your time, for your patience, and I leave the stage to Louise for his talk. Thank you so much.